right, so this page 273. We're going to highlight first adding functions, some notation stuff. When we're adding functions, I really like it when it's written like this because I think it makes total sense. I don't like it quite as much when it's written this way. But when it's written in brackets first, f plus g brackets x, you have to know that that's the same thing as f of x plus g of x. So that's some notation stuff. Then all that's happening is you are adding the y values. So here they have, from the graph, f of 2 plus g of 2. Well, f of 2, that's our red graph, that's equal to 2. Because f of 2 says, what's the y value when x is 2? And g of 2 says, what's the y value for g of x when x is 2? And then we look at our blue graph, and that one's at -1. So if we go 2 plus -1, we get 1. And on our new graph, that's just adding up all those y values. I want you to notice on that green graph that the green graph's domain starts at -2 because the graph of the red function, f of x, starts at -2. So the domain when you're adding two functions is where both of them exist. So if one of them exists and the other one doesn't, then the domain for the adding won't exist either. So that's why the domain of h of x is greater than or equal to 2. Some more notation stuff. Subtracting. So again, this is the nice notation, but you also have to be prepared for seeing this notation as well. Again, all you're doing is subtracting the y values. So we know that f of 2, when x is 2, y is 2. When x is 2 on the blue graph, y is -1. 2 minus a -1 will be 3. And again, you're just dealing with the y values. The domain for subtracting is the same rules as the domain for adding. Both functions have to exist in order for you to add them or subtract them. And so the domain will be the overlap of both of them. What would happen if I had one square root graph like this and one square root graph like this? And let's say it went from -3 all the way to 2. If you added or subtracted those, what would the domain be? And let's say the blue one's f of x plus the red one's g of x. What would the domain be of f of x plus g of x?
X has to be greater than or equal to -3 or less than or equal to 2.
Right. So x is between -3 and 2. And it would have those equal signs because that's the only part that both of those functions exist. Multiplying. Notation-wise. And we're going to, so this is a normal notation. Sometimes you'll see it with a different font X. So you'd be like, oh, I recognize that font. That means multiplication. And those other fonts, they mean X's. Have you noticed? If they have a multiplication font is always sans serif. Do you know the difference between serif fonts and sans serif fonts? So like Times New Roman, this looks like this is Times New Roman. This is a font that has serifs. In other words, you see this T? It's not just straight across like this. It adds like, ooh, fancy little dingles. I don't know if that's the word for those. Right? Or fancy serifs. I guess that's what they're called. So multiplication is always a sans serif, and often variables are often serifed. I don't know how to, we don't often write that way. Nobody handwrites or prints with serifs because it would take forever. Some people do. Have you ever seen some people's handwriting? They like add extra little stuff. It takes them forever to write their name? No? Okay. Anyways, so you could have it with like a times sign like that. I've also seen it with this one being fancy and this one being with the woo, all the extra things on there. So we can see whatever multiplication symbol we're used to, although we tend to more often have the dot, now that we're dealing with algebra, not to confuse the multiplication sign with an X. Again, anytime you have this notation, so sometimes you'll have, like, I'm going to look at this graph, and I want you to tell me what that's equal to. Zero. I was going to say you're all right because I haven't heard nothing yet. 0. How do we do that? Well, what I would do first is whenever you have this notation, change it. Change it to this notation. That's much easier for you. And f of negative 2, that's on our red graph. That's 0. G of negative 2, that's on our blue graph. That's at 3. 0 times 3 is 0. So change the notation into the notation you're more familiar with. Now, what's going to happen when you do f of 2 times g of 2? Well, f of 2, again, is 2. G of 2 is negative 1. If you multiplied those together, you would get negative 2, and there's your green graph. Some things that we noticed about the functions from before that I want to point out again. Okay? You see those 2 points? That was where either the original red graph or the original blue graph was 0. And 0 times anything is going to be 0, so that's why the green graph is 0 there. So those are some important points. Other points that can become important. Notice this point here and this point there. What's special about those 2 points? Well, if we go from the left, the first point is on the blue graph. Why is it on the blue graph? Because the red graph is 1. And 1 times anything won't change that value. So that's where your green graph will intersect the blue graph. And the next point, your green graph is on your red graph. And notice that your blue graph is equal to 1. Because 1 times anything is itself. So those are some key points. Some other things to notice. In this whole section, both the red graph and the blue graph were positive. So your green graph is positive because you know a positive times a positive is positive. But after this, our green graph is negative here because our red graph is positive and our blue graph is negative. So positive times a negative is negative. Again, just like before, the domain is where both domains intersect. So that's important to see for multiplication. So for adding, subtracting, and multiplication, the domain is just where the 2 intersect. Dividing gets a little bit different. But we won't do dividing until we're done example 1, and we'll do example 1 right now. So we're going to draw a quick graph of these. F of x, I'm going to draw here in green. F of x is x plus 2. That's just a straight line with a slope of 1. And g of x I'm going to do in red. That's your absolute value. Remember that from transformations? That graph looks like that. State the domain and range of f of x and g of x. Well, they're both everything. For the green graph, the range was everything. For the red graph, the range is y is bigger than or equal to 0. So both of them have a domain of everything, but their ranges are different. Now they want to see what happens when you add h of x equals f of x plus g of x, and then we're going to write an explicit equation for h of x and determine its domain and range. So let's start adding some y values, because this is going to be an interesting graph in the end. First of all, you know that these points on here are like so. And you could label some points on this graph as well. In fact, if you wanted to, we could make a table of values of both f of x, that's our green graph. We'll start at -3 and go to 3, just to get a lot of values. And we could make a table of values for g of x, which is our red graph, and then find out what h of x is going to equal. So f of x, -3, you'd have -1, 0, 1, 2, 3, 4, 5. G of x, you'd have 3, 2, 1, oops, I want to change that to red. 3, 2, 1, 0, 1, 2, 3. And again, what happens when we add functions? We're adding our y values. So on h of x, if we want to figure out what our y value was when x is -3, we just have to add -1 plus 3, and we get 2. And we get 2. And we get 2. And we get 2. What do you think the next one's going to be? 2. No, it's 4. Sorry. Okay, so 6 and 8. So if we plot this graph, it looks like this. Boom, 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 boom. And then after that, it goes at 1, 4, 2, 6. Oh, that is a weird equation for that, or a weird graph. Now, how do we write an equation for this graph? Well, this graph sort of has, well, it does have two pieces to it. So the way that we write the equation for this is h of x is equal to, put a big squiggle bracket, and we write the two pieces. Can you see that for a lot of the graph, it's just equal to 2? When does that happen? That happens whenever x is less than or equal to 0. Does that make sense? How I wrote that? And then, what is the equation for this graph here? Well, it has a y-intercept, it's a line. It has a y-intercept of 2. Looks like I go over 1 up to a slope of 2. So 2x plus 2, where x is bigger than 0. When you write a piecewise function in two parts, one part, notice right here, this has an equal sign, but this part doesn't. You have to decide. It really doesn't matter which one you put the equal sign on, unless the actual graph was broken, then it would matter. But in this case, where they're touching each other, one of them will have an equal sign and one of them won't. How could we have done this algebraically? Well, the key to doing this algebraically is really to realize that your f of x function, which is the absolute value of x, is really two lines put together. Does that make sense? That the absolute value is two straight lines put together? What are those two straight lines? Well, one of them is minus x. That's when x is less than or equal to 0. Because it's a straight line with a slope of -1, but you only have that line when x is less than 0, and it's equal to x when x is bigger than 0. Now, algebraically, what happens, did I write that, was that f of x? No, I got them wrong. That was g of x. Just make sure our notation is right. Now, what happens algebraically, when we do f of x plus g of x, well, it's going to have two parts to it. It's going to have this part when x is less than or equal to 0, and this other part when x is bigger than 0. When x is less than or equal to 0, f of x was 2x. What was it? It was x plus 2? X plus 2. F of x was x plus 2. And then you have to add g of x, which is minus x at this point. In the other one, f of x is still x plus 2, but when x is bigger than 0, g of x is positive x. Can you see that when I add these together, that this first equation, when it's simplified, is equal to 2? Because the x's would cancel out. And the second equation, when you add the x's together, you get 2x. Have you ever seen in grade 11 or grade 10 absolute value written this way? No? Kind of?
I remember the whole, I forget what was the context, but I remember the one side had to be equals and the other
Okay.
that sort of thing.
Now, does it make sense? If inside here I put negative 3, then I'm following this rule here, and it says multiply by a negative, and negative times negative 3 makes that positive 3. But if you did the absolute value of 6, well, you know that's equal to 6 because it falls under this. It's just the same thing as what's inside. If what's inside is negative, you multiply it by a negative to make it positive. And that's the same thing that that idea is trying to say. So there we have the explicit equation for this new graph. Now in part C, it says take both of these graphs and multiply them. Well, if we multiplied them, so I'm going to just take this that we have here away now, and I'm going to redraw H. I'm going to redraw this. I'm going to take this graph off. And now we're going to do P of x, the product. Now, if the product, you take negative 1 times 3, this would be negative 3. 0 times 2 would be 0. 1 times 1, 1. 2 times 0, 0. 3 times 1 would be 3. 4 times 2 would be 8. And 5 times 3 would be 15. So when plotting this, we have 0 there, negative 3, negative 3, negative 1, 1. 0, 0, 1, 1, 3, and 2, 8. So it kind of looks like this and like that. Again, a pretty weird looking graph. So what's happening with P of x? Again, if we use our equations here and we take f of x and we multiply that by g of x, we have to look at those two pieces. If I took when x is less than or equal to 0, f of x is x plus 2, and g of x is a negative x. From that, well, I'll simplify it afterwards. And when x is bigger than 0, f of x is x plus 2, and g of x is x. So if we multiply both of those out, we get that p of x is equal to negative x squared minus 2x and x squared plus 2x when x is less than or equal to 0, or when x is bigger than 0. It makes two parabolas. Can you see from our graph that we have one parabola here, and the other parabola is here, but it doesn't even get to its vertex? So complicated in that the final equation that we get isn't pretty, isn't nice looking, and this is a new idea right here to know that the absolute value has to be written in pieces. Most of the time, you'll get functions that you can just multiply, and they won't have pieces. But if you do get the absolute value, you're going to have to separate it into different pieces. Questions you can do for practice for this one are 3, 5, and 10. We'll do one more example, and then I'll give you some time to try both.